Hi there. This video is for section 7.1. I'm going to show you how to find integrals using the method of integration by parts. And this is a method that does not use technology. So I'm going to start off with sort of an idea of why the formula is the way it is. It's basically based on the kind of differentiation rule for the product of two functions. So we're going to look at the rule called the product rule for the differentiation of two functions being multiplied. And we're going to integrate both sides. So do the integral of the left-hand side, integral of the right-hand side. The integral or the antiderivative and the derivative are inverses or opposites of each other. So they will undo each other or cancel, as a lot of people say. So I end up with just u dot v is equal to the integral of the right-hand side, which I can separate into two parts because they're being added together. And then if I just move things around, if I move like the uv prime over here and I read right to left instead of left to right, I get this formula right here, which is our integration by parts formula. The integral of u times v prime is equal to uv minus v u prime. And just to be clear, like the u and the v are the two things being multiplied together in the differentiation rule, but in the integration rule, it's u times the derivative of v. So u times the derivative of v is equal to u times just regular v, which is the integral of the derivative, minus the integral of v times the derivative of u. And sometimes it's written with dv's and du's instead. So depending on how you read this or how you like to remember it, either one will work. This isn't really a standard proof. If you show this to your calculus teacher, they may say, well, it's missing a few parts. I'm just trying to give you an outline here. It's missing a bunch of dx's and things like that. But this is how we get the formula that's called integration by parts. Now, the textbook and math people will say this is the method of integration by parts. It's not really a method of integration. It's just a fancy algebraic simplification. So we're basically using algebra. It's a kind of substitution. So we're going to be substituting things in for here and here and converting from one variable like x into a different variable. So it's a type of algebraic technique. And the goal is not to find the integral. The goal is to change this into a simpler integral that we can use our formula sheet of known integral formulas to do. So the idea is do this method of simplification and end up with an integral which we can now do using our known formula sheet. So that's our mission, and that's the way you sort of need to frame this. Let me show you with an example because it'll be easier to see what I'm talking about. So let me do that. My first example here, I have x times cosine x dx, and you can kind of see the two things being multiplied, the x and the cosine x. We actually need to have all of the integral like in our two functions being multiplied, and the two functions are u and either v prime or dv. I'll use the dv one because I think it's a little clearer about which one is the function and which one's the derivative, things like that. So u can be part of this. Let's say it's x part, and dv will be the rest. Now the rest is cosine x dx. So make sure you have that dx over there. I know it seems like it doesn't matter that much, but it just, as I've said in previous videos, it matters more and more as we do more sophisticated techniques. So once we get this, we're going to have to find the other parts. So we have the u and the dv. We have to find v, which is the antiderivative of dv, and we need to find du, which is going to be the derivative of u. So we need to sort of take the u thing and differentiate it, take the dv thing and integrate it. So just to be clear, if I have dv is equal to cosine x dx, I just integrate both sides. The integral of dv is v, and the integral of cosine x dx, well, that's a formula. If you look on your formula sheet, which hopefully you guys have somewhere handy, you can see that the integral of cosine, number 8 on my sheet at least, is sine x plus c. So we get sine x plus c. Now, it turns out we don't need the plus c's in the middle of our problem because we're just going to get a bunch of plus c's that we're going to put together to be a plus c at the end. So there is kind of a plus c over here, but you don't really have to put it in the problem yet because we're just going to get a big plus c at the end. And also to be clear on this derivative thing, du, u doesn't turn into du. We differentiate both with respect to dx. That's actually what's happening. We're differentiating the left-hand side, differentiating the right-hand side. Just like on the previous part, we integrated the left-hand side and integrated the right-hand side. Here we differentiate. The derivative of u is called du dx. And the derivative of x is just, well, 1. And then we move the dx on the other side, so we get du is equal to 1 dx. Now, a lot of people kind of skip the step in the middle, and I'm okay if you skip that step, but that's what's really happening. You're differentiating it, getting du dx, and then you're just solving for du. All right, so just to be clear, we know our u thing, it's x. We know our dv thing, it's cosine x dx. And we know our du, it's 1 dx, and we know our v, it's sine x. So we have the different components to now do our formula. So our formula, I'll write it up here just for reference. It says integral of u dv is equal to u times v minus integral of v times du. And let me go ahead and fill in the things. So u was x, and dv was cosine x dx. And that just verifies that on the left-hand side, we have what we're trying to find. So that's correct. And then we get u times v. So u is x. V is over here. It's sine x. And they get minus the integral of, that's v. V is over here, sine x. Times du, and du is 1 dx. So that's how the integration by parts formula works. You have one part of it called u, the other part of it called dv. Those two together have to be the entire integral, and then you find du, you find v, and then you plug it into your formula, and hopefully what you get is simpler than what we started with. So let's see what we get here. Well, on the left-hand side, we have x cosine x dx, which is just the original problem. So that's the same as what we're trying to find. So if we find this, we're finding the answer to what we're looking for. On the right-hand side, we have x sine x, which we don't need to anti-differentiate or anything. It's just x sine x. It doesn't have any symbols in front of it, so that's just what it is. And then we get minus an integral. So this is the thing we have to decide whether it got simpler or not. Sine x times 1 dx is just sine x dx. So I always invite students at this point just to take a pause and look at the new thing they have. This is the new thing. And this was the original thing up here, the old thing. Is the new thing easier to anti-differentiate than the old thing? If the answer is yes, you did good. If the answer is no, you need to start again and try something different, because the whole idea is that it gets easier. The antiderivative of sine x is much easier than the antiderivative of x cosine x. I know this for sure because if I look on my formula sheet, there is no formula for x cosine x. You won't find it on any reasonably sized formula sheet, but there is an antiderivative of sine x that is on the formula sheet. So we've converted it into something which we have as our known integral. So that means, yeah, we did a good job. So let's go ahead and finish this problem. So the integral of cosine x dx is equal to this x sine x minus the antiderivative of sine x. The antiderivative of sine x is negative cosine x. And now we'll put in our plus c, which is the addition of previous c's. If you want to put plus k, if you want, just to say it's a different, it doesn't really matter. It's just some constant. So don't get too wrapped in there. Just remember to put a plus c at the end. And then I do ask you just to do the bare minimum of combining things together that are easily combined together. So a negative, negative, that makes a plus. Cosine x plus c, and that is the antiderivative of our original problem, the x cosine x dx problem that we started with. And that's a demonstration of how integration by parts works. All right, so we're going to do some more complicated versions of integration by parts, but they all rely on the same formula. The integral of u dv is equal to uv minus integral of v du. So we're going to be using that formula and just see how it gets more complicated as there's more twists and turns in doing this. One of the basic things that makes this more complicated is that, like for this problem, I just said, hey, let's let u be x and let dv be cosine x. Could we have done this by choosing the other way around. Could I have chosen u equals cosine x and dv is equal to x dx? I mean, there's no reason why I couldn't split them up in a different way. Will this work, right? Does this work here? Does this work? Let me say, does this work also? Because we know the one that we chose worked. I mean, I chose it. So I chose it because I know it works. And I'm not going to demonstrate on this one. I'll demonstrate on one of the other problems. But when you choose u is equal to cosine x and dv is equal to x dx, the integral you end up at the end is more complicated than what we started with. And I'm going to let you do that if you'd like to see. You'd like to put in this u and this dv and find du and find v and put it into the formula. And you will see, oh, the new thing I got is definitely not easier than the old thing I got. And so the first thing that makes things more complicated is that it's not always clear what to choose for u and what to choose for dv. Sometimes it doesn't matter and they all work. Sometimes only some of them work. So be prepared that you're not always going to choose the best one, the best decomposition in U and DV the first time. It takes a bunch of experience and sort of a little bit of practice to be consistently getting them at least maybe 90% of the time or better. That would be a good goal for you at the end of the course, is just to be usually correct. It's very, very challenging to get it always correct. It's just there's so many things to keep track of and variables and such that you're gonna have to learn through experience. You got what I'm saying? All right, let me stop yakking and go on to another example. All right, so here's an example of x ln x, and we just did x cosine x, so we can see two things being multiplied. So I'm going to let u be one of them, like the first thing, and I'm going to let dv be the second part, which is ln x dx. Right, so it's similar to the cosine deal. And then I got to find the derivatives. This is du dx is equal to 1. Or, I can move the dx over and just say du is equal to dx. Kind of do it in one step. If you're not comfortable doing it in one step, that's okay. You can do it as many steps as you like. I just think a lot of people are going to be saying, oh, why don't you skip that step? And I said, okay, I'll skip it. So I need to anti-differentiate ln x dx. Depending on what formula sheet you have, ln x may or may not be on that sheet. I do have it on my integral sheet. The antiderivative ln x is x ln x minus x, plus c. So I'm going to do the x ln x minus x according to the formula sheet. And I'll just leave out the plus c. And then, so our formula, uv is equal to the integral, I got to get my formula right. U dv is equal to the uv minus v du. All right, so what do we get? We have a u and we have a dv. So that's this thing over here, x ln x dx. And we should quickly verify that that is exactly what we started with. So we know we're using the parts that make the whole. And then we get u times v. Here's the v down here. So I get x times x ln x minus x. And then minus the integral of v, which is x ln x minus x. And then du is over here, so du is just dx. So kind of like this. All right, so that's the integration by parts formula. Let me just do the minor simplifications. I'll distribute this x squared ln x minus x squared. And then here I have the integral of, there's nothing I can do really here, just x ln x minus x. So once again, once you do the formula, the integration by parts, the first thing I really would like you to do is look at the new integral. This is the new one. Compare it to the old integral. The old integral's up here. Did it get simpler? I think the answer is no, because we still have x ln x like we had in the original version, and we also now have a minus x. So like we got even more stuff to anti-differentiate now than we had in the beginning. This is not simpler. Okay, so this is what I was explaining in terms of sometimes it just seems like this is a good choice for U and DV, and it just doesn't work. It doesn't give you a answer that is simpler. So we need to do something different because this method of simplifying didn't actually simplify. So maybe this is the one we should try to switch around. So where integral is x ln x dx. And before we chose u is equal to x and dv was the ln x dx, let's switch it around. Let's choose in this case, get my blue here, u is equal to ln x. And the dv is the rest, which is x dx. Okay, so then we have to take the derivative, which is du dx. I'll just write the dx on the other side. The derivative of ln x is 1 over x dx. And here I have to antidifferentiate. The antiderivative of dv is v, and the antiderivative of x is x squared over 2 plus c. So that would be my v function. So our formula over here is the integral of u dv is equal to uv minus the integral of v du. We have all our components, u and dv and du and v. We just put them into the formula. Okay, so u dv is equal to u times v minus the integral of v times du. Du is right over here, 1 over x dx. Okay, time to clean up. Oh, we need to just make sure, did we do the right thing? Is this the same as this thing? Yeah, even though the x was in front and the x is after, it's the same thing. So yeah, we're doing the right formula. If this comes out, then we know we have the right answer. In fact, if you want, you could just move the x in front just to like be more traditional. It doesn't really matter, right? Because it's the same integral. All right, over here we have, well, that's just, I'll put the x in front again, just for the tradition, but we have x squared over 2. And then we have our ln x. And then minus, and here we have x squared on the top, so it simplifies with x on the bottom. I'll bring the 2 on the outside of the integral, and I'm left with x squared divided by x is just x dx. So once again, here's the new guy. Here's the old guy. Is the new guy simpler than the old guy? This is supposed to say new. And I would say yes. Antiderivative of x is very simple. In fact, we already did it up here. We already antidifferentiated x and got x squared over 2. So I know we could do that one. So this did get simpler, right? So now we're happy, right? And we can finish the problem. Okay, so what do we get? We get, well, we get our x squared over 2 ln x thing. And we also get this 1/2, and the antiderivative of x, as we know, is x squared over 2. Let's put in that plus c that we neglected to put in before. And our final answer, I've just combined together those 2's together, x squared over 2 ln x minus x squared over 4 plus c. All right, so there's an example where it's, not always going to be your first guess as to the best choice for u and dv. And I set up the second one so that it looked a lot like the first one, which was x cosine x. This one was x ln x. And it turned out that using a very similar one did not result in happy face, but switching things around did. So that's what I was trying to get across with that second example. All right, so let me show you what I had in mind for this third example. So for the third example, this is kind of a classical one that kind of Calc 2 instructors routinely show. This is the integral of ln x dx, which is on our formula sheet. So we can be done just by looking it up on the formula sheet. And it's the one over here. The integral of ln x is x ln x minus x plus c. So we can be done. But let's pretend like we didn't know this formula. A lot of formula sheets won't have number 6 on there. So suppose you had something like this that was not on your formula sheet, or you didn't remember it, and you actually had to anti-differentiate it, by hand, not by looking it up on the sheet. So the reason why I want to show you this is because it doesn't look like there's two things being multiplied. It's just ln x, right? So what's the deal? How is this integration by parts, which is sort of meant to be the u times dv thing? Well, we're going to let u be ln x, as we did in the previous problem. And dv is going to be the rest. So dv in this case, well, what's the rest? Well, the rest is just dx. And if that makes you uncomfortable, you remember there's always a 1 in everything, right? It's just 1 dx if you want to think of that. So this is just 1 dx, right? There are two things. One of them is just 1, which is not very interesting, but we can see there are two things there. And the derivative of this thing, as we have seen before, is 1 over x and dx. And the antiderivative of v is just x. And then we can do our formula, u times v, which is ln x, or no, u times dv, ln x. I stopped writing my formula because I'm going to say I don't have to write my formula every time, but now that I didn't write my formula, I messed it up. So I guess it means I have to write my formula again. All right, so the formula is u dv equals integral of u dv is equal to uv minus integral of v du. Okay, so let me just keep that guide there so I don't mess up again. That little mark there. Okay, make it look a little bit more legible. Okay, so integral, what's u? U is ln x. dv is just 1 dx, or just dx. And I get uv. So u times v is ln x times x. And then that's minus the integral of v du, v being x, and du being this guy right over here. This is du, this is v. So v du is x times 1 over x dx. All right, so let me move up here a little bit and clean it up. Maybe I'll change color to make it pop out a little bit better. So I get the integral of ln x dx is equal to, this would be, I'm going to run out of room. I don't have good spatial sense here, so I'm going to have to, because my other stuff's over here is getting in the way. So a little bit of my visual difficulties, but I got it here. So I'll just go straight across. I'll go straight across. So I get the integral of ln x dx. Now my pen is not cooperating, so everything is going good for this video. Integral of ln x dx is equal to, well, we got ln x times x. And then we got minus a new integral. So let me make some more space here on the right. Over a little bit like that. So I get minus, well, x times 1 over x is just 1. So we get 1 dx. All right, so is the new integral simpler than the old integral? Well, the new integral is just 1, and the original integral was ln x dx. So yeah, 1 is way easier than the other one. So I get, well, let's be traditional, put the x in front of the ln x. So we get x, ln x. And the integral of 1 is just x. And then let's put our lovely plus c at the end. And this is the formula that was on my formula sheet anyway. I was trying to demonstrate how sometimes it's not like obvious that there's two things being multiplied, like what can I have? And the second thing could be one, right? So I just wanted to throw that example, and this is a very classical example for a Calculus 2 class. So I do the classics for you. And what I wanted to also show as sort of a little sideways or maybe deeper idea is that in general, we're going to be splitting these things into U and dV. The U thing we're going to be differentiating, and the V thing we're going to be integrating. And hopefully, when we differentiate the U, the new thing will be simpler than the old thing. So when I had U equals ln x, the new thing was 1 over x. And although fractions aren't necessarily great, they're usually way better than logarithms. So 1 over x is simpler than the original ln x, right? Or the other thing to keep in mind is we have to be able to anti-differentiate dv, right? dv has to be anti-differentiable in some easy way. Otherwise, it's not going to get simpler, right? It's going to get much more complicated, and sometimes we can't even do it. So a general guide is when I'm choosing u, is it getting simpler when I differentiate it? And when I'm choosing dv, is that something I can reasonably easily anti-differentiate? And it gives me something which I can still work with. So I just want to kind of show you those broad sort of things to think about when you're getting good at picking the U and dv. I'm going to make this a two-part video. I'm going to try to fix my stylus and make the part 2 with the rest of the examples. All right, so hopefully so far the video is helpful, and you can watch part 2 if you want to see some more complicated examples. I'm going to go into like a mixture of U substitution and integration by parts, where you have to use multiple methods. So if you're interested, you can watch the part 2 video. Okay, doke.